Hi, this is Ariel NY4G again with another video, and this video is about some of the cool things you can do with a NanoVNA. What is a NanoVNA? Nano meaning very small. Nanometer is 1/1000th of a meter in size, so it's just the prefix itself saying it's small. But it's a vector network analyzer, so it has a lot of capability. VNA meaning vector network analyzer, measuring both amplitude and phase. That's what a vector is, or a phasor is in RF design, and it's good for evaluating RF networks and AC circuits. Lab-grade vector network analyzers are very expensive, and the calibration standards alone can be upwards of $2,500. Of course, it has more ports or channels, it has a higher sampling rate, and a higher frequency range. Along came the NanoVNA, and it's selling for between $50 and $130, depending on which version you buy. There's only 101 points per sweep on the H version, and there are 401 points per sweep on the version 2. On the H version, there's a 900 megahertz upper limit, and on the version 2, there's a 3 gigahertz upper limit. And there are 2 channels or ports, and there's a computer interface program that's open source. And there are plenty of YouTube videos that go deep into the basics and nuances of the NanoVNA. And a good one to look for is videos by W2AEW in YouTube. Well, here's my NanoVNA that I'm showing you here. In it's a H4, the 4 meaning it's a 4-inch display, and on the screen it can display up to 4 parameters. Both channel 0 and channel 1 can be displayed in various formats. And what cool things can one do? One of the things that's every ham seems to be inclined to do is to measure the standing wave ratio, or SWR, of an antenna. And for example, we will be measuring one of my antennas, NY4G end-fed half wave. You can also tune a non-resonant multiband antenna SWR in the field, for example a Norcal Doublet, which is a multiband non-resonant antenna, and you can evaluate a low-pass filter. And I built one for using it on my whisper transmitters. And of course, when you build it, you're trying to evaluate whether you built it right and is it behaving as expected. Another thing we're going to go into is the measurement of the efficiency of an end-fed half-wave transformer. And this one we won't get into, but I just wanted to put it on the list. It can do a neat thing like measure the length of an unknown length of coax cable, or if you know the length of the coax cable and you want to find out if there's anything wrong with it, then you'll find the fault in the that will show up as a fault in your NanoVNA display. You can also measure the choking impedance of an RF choke. So let's start with evaluating the standing wave ratio of an antenna. And you'll only need one port for this, the reflection port, which is channel 0, or port 1 in some VNAs. And you're only going to be measuring the reflection parameters, because the standing wave ratio really is measuring what the reflected power is that's returning back to the source. So it's measuring the reflection coefficient, return loss, or standing wave ratio. They're really just different names for the same thing. just measurements of the power that's coming back. And some understanding of logarithmic math is needed if you want to go deep. And I have some video clips that I will be going through. So our first task here is to analyze or evaluate the SWR of one of my antennas, an NY4G and fed half wave, and this is the setup. We have the feed line going into the room there, that point where I was pointing, and this is the antenna itself hanging on a mast that's attached to my deck. I don't know if you can follow the wires, and at the far end it's hanging down as an inverted V, and the termination of the inverted V, the end of the other end of the wires into the trees. And the dips correspond to the different bands, which are the different harmonics of the fundamental. The first one being 40 meters, and then 20 meters, 14 megahertz, 15 meters, 15 megahertz, and 10 meters. Let's look at the SWR distribution within the 40 meter band at first. So we look at our NanoVNA and try to select the stimulus start, and we'll start at, I'm pointing here to 6.8 megahertz. The band really starts at 7, but we're trying to capture the dip, and then we'll stop at 7.3 megahertz, which is the end of the band. And as you can see, most of the band is, the lines are, the first line is 2 to 1, so that crosses 2 to 1 right at 6.8 megahertz, and then the sweet spot is right around 7.060, which is in the CW portion of the 40 meter band. And here I'm looking for a minimum using the search function of the NanoVNA. Here I'm going to try to look into the where it crosses 2 to 1 again on the high side, and it crosses 2 to 1 on the high side at 7.225 megahertz, which is just a little bit shy of the end of the band, the 40 meter band, which is at 7.3. So we're 75 kilohertz shy of getting the entire band under 2 to 1 standing wave ratio. So let's look at the next band. And here I am trying to use the touch controls to select the next band, being 20 meters, and we'll start at 13.9. The band actually starts at 14, but we're trying to capture the dip, and we're stopping at 14.5. The band really ends at 14.35 megahertz, but that's just, I guess, trying to capture the entire band and have some leeway at the ends. You can see the entire band is below 2 to 1 standing wave ratio. Let's look at the 15 meter band. and we'll start at 21 megahertz, which is the start of the 15 meter band, and we'll stop at 21.45, which is the end of the 15 meter band. And you can see the SWR is also below 2 to 1, and the dip is actually into the sideband portion 15 meters. The lowest SWR, which is close to 1 to 1. And looking at 10 meters, 28 megahertz being the start, and stop being 29.7 megahertz. And you can see that it's above 2 to 1, below about 28.5 megahertz, and see where it crosses over here. And so a portion of the 10 meter band is going to need some sort of tuner if you want to be below 2 to 1 standing wave ratio. It is a wide band. It's almost 2 megahertz wide. Next is the Norcal Doublet. A Norcal Doublet is fed with a wire feed line instead of a coax. So and how you construct it is you have two radiators that are 22 feet long on each side, so it's a 44-foot overall length antenna. It's a flat top, and it uses a ribbon cable, and you don't use the inside two cables, you just use the outside two cables. When you split the cable, you split it so that the 22-foot legs become the radiator, and the ones that extend down on the outside become the feed line. And I'm using this MTech ZM2 as a tuner, which has balanced line inputs as shown as by the red and white banana plugs there. And I'm going to play this video. Now let's try to adjust this antenna with this NanoVNA using the knobs on the controls, on the two control knobs, to see if we can move the dips. These are the characteristic dips in your Norcal Doublet, and we'll see if we can try to tune one of the bands using the controls. There happens to be a dip near 80 meters, and so that's the one that we're going to try to adjust first to see if we can get it to resonate. And so we'll have our start at, I guess we can start at 3 megahertz, and we'll stop at 4 megahertz. You see there's nothing there, so there's no resonance yet. We have to turn those knobs. Oh, there we go. There's a dip. Now it's just a matter of adjusting that dip to be near where you want to operate on the 80 meter band. And here I'm seeing what the frequency is of that dip, and it's turning out to be about 3.4 megahertz. So we have to move it to the right a little bit by adjusting those knobs, turning it just a smidgen to move that dip to the right. It's closer, it's 3.47, so just have to move it a little bit more. So in the field, if you have this tiny tuner, which is not very heavy at all, and you have this lightweight Norcal Doublet, you can use that as an antenna. And here we go. We're just about zooming in on getting it close to 3.5 megahertz, and we're ready to go. Next thing we'll look at is how to evaluate the low-pass filter that I built, and this is a 3-band low-pass filter, and one would have to move the jumpers to select the band that I want to evaluate. And here's a close-up of the low-pass filter with the jumper on the upper portion. I believe that is 80 meters. I'm not sure if the video is going to be at that point though. Let's see. Okay, no, I guess we don't have, these are just snapshots. So what we're looking at is the through what goes to S21, which is the transmission loss. And so what you want is very little transmission loss for your filter. And so what you want is this yellow line to see how it's dipping. The blue line is the log mag of the reflection port, which is a measure of the SWR, and this green trace is a Smith chart, which gives you the complex impedance as you go from as you move this marker around. So this is the 80 meter low pass filter. So you can see that the marker's at 4.4 megahertz, and just past that it starts dipping, which means it's not allowing the signal to go through, because you're getting a lot of reflection, you're getting a lot of transmission loss as you go much above 4.4 megahertz. So this is the 80 meter low pass filter. And this is the next one, it's the 60 meter low pass filter, and you can see that there's very little transmission loss until you get to about 6.4 megahertz, and of course 60 meters ends at around 5.45 megahertz. So it starts attenuating anything that goes much above that. And this one is the 40 meter low pass filter, and you can see the marker now. It would start dipping past 7.5 megahertz. And so these low pass filters are behaving as expected. So it looks like I made the right turns on the toroids and put in the capacitors the way I was supposed to, because the filter is behaving as expected. Next thing we're going to look at is the measurement of the efficiency of an end-fed half-wave transformer. And one may ask why. Because I like playing with antennas, and I want to compare the effect of different winding ratios of secondary to primary, varying capacitances, varying the shape, size, and composition of the ferrite core, whether that has an effect on the efficiency, because I'm trying to get the best efficiency I can out of a transformer. And we will need both ports for this, and we will be needing to do logarithmic math after extracting the necessary data. And so here's the NanoVNA display with all the ports that I need connected. This green line is the through port, S21. It measures the transmission loss, the transmission coefficient. And this yellow line here at the bottom is the log mag of the reflection coefficient. So it's getting the SWR. And the data we'll be collecting for our calculations is S21 and SWR. And this is my test setup. I have connected one of the ports to the feed point of the transformer, and I have rigged this resistor. These resistors in series make up for 3200 ohms, which is the same resistance as something that will have an antenna that will have a transformation of 6 to 4 to 1 to the 50 ohm that I want. And so port 1 is connected to the feed point, and port 2 is connected to the resistor termination. And this core is wound as a 24 to 3 secondary to primary with a 100 picofarad capacitor. And so we get the data. First, we calibrate the NanoVNA by putting on a short and open 50 ohm load and a through calibration, so that we make sure that our data is good. And this is sort of a sketch of what we're measuring. We're measuring the efficiency. We're trying to measure the efficiency, which is we're trying to measure how much power is consumed in this transformer as heat and not used to be radiated in the antenna. So this is the equation for efficiency, which is P out divided by what's going in minus what's reflected. So that's sort of a controlled volume of what we're trying to get. And so we get all our data, and it's all in a spreadsheet, and we collect the data for different frequencies. And in this case, we're looking at the S21, which gives us the once we this adder here is the effect of the attenuation through the resistor, which is the attenuation through the simulated antenna, and it gives us insertion loss. The log mag of the reflection coefficient is this one. That's another data point that we get, and we check that against the SWR to make sure they agree. And based on all this, one can do the math if you know the equations that give us efficiency. And the efficiency, for example, at 80 meters is 96%, and it stays above 90 all the way up to 17 meter band. It drops down to just below 90% on the 50 meter band. So there you go. That's how you measure the efficiency of a transformer. And so these are the results of, you plot it all on a graph graphically, so you can see what the results are. You can compare results. And here I'm comparing it to the results of previous measurements I made to an LNR 402010 transformer. And so this is the NY4G end-fed half wave, and this is the LNR 402010. And so if you've stayed this long, rather lengthy video, so anyone that has questions can put the questions into the comments section. I'll try to answer them as best I can. Thanks for watching, and we'll look for you in the next video.